So welcome to this last lecture in terms of contents about intentional systems, the attempt to build a neural dynamic model of intentional systems. So this is work that's inspired by philosophical concepts. So I think the cognitive scientists among you will be kind of interested, or some of you are a bit more philosophically minded might be interested by that. So we were inspired by Searle's analysis ultimately of consciousness and approximately of intentionality. Of course, a concept that in philosophy has been discussed a lot, and we're trying to use these concepts as a way of talking about what it could mean to understand the mind on a neural basis. So how would the mind emerge from neural processes? In fact, in one of Searle's books, he challenges cognitive scientists by saying, you could try to build intentional agents and that way sort of test the concepts. And that's actually what we did and tried to do. And it gave us a very good understanding of also of the difference between defining philosophically and logically what these different concepts mean in talking about the mind versus what they mean for neural processes, and I'll highlight that. So our approach is to use the philosophical concept of intentionality as a way of talking about the mind and saying mental states are intentional states. So I have to tell you that the philosophical concept of intention is a little bit more general than the concept, or more abstract, the real daily life language concept is, intention as a sort of a desire, a will, something you intend to do. That's a common term that is included. I'll explain that in a moment, but the philosophers talk about it more generally as the capacity of an agent or a nervous system or a person of having mental states that are about things in the world. These can be about objects in the world, things that we perceive, but they can also be about the agent's own body. It can ultimately, very subtly, also be about other mental states. Like if you think about yourself or about a thought that you have when you do metacognition, or when you think about a memory, then you have an intentional state, and it is about something that is actually in your mind, or it could be physically another state of the nervous system. And to make this more concrete, you have to think of the two directions of fit in intentional in philosophical terms. So the world to mind direction of fit is the idea that you have a mental state that is about the world, and it would be satisfied, it would become true if the world changes to fit that state of the mind. So that is the more common idea of intention, like a motor form of intention. So always talks about the intention to lift your arm, and when you then have brought about that action, your arm has been lifted, then the world fits your intention, fits your mind, and you have achieved that intention. So the condition of satisfaction of that intention is that the arm has reached the state that you intended, and that it was you, the agent, who caused that state to change in that way. So that's just the more glorified way of talking about motor intention. You see other examples in a moment. While the other direction of intentionality is not commonly called intention in daily life, it's actually typically called perception or memory or representation, knowledge, and so on. So that's the case where the intentional states consists, is about the world in the direction of fit, that it has to fit the world. So the world is given, and you have to have a mental state that fits that. And the condition of satisfaction is when that fits. For instance, if you see an object, I have here this tube. If I have some mental state that is the perception of that tube, then that percept must fit that. So in many cases, you might find that trivial. It isn't. At some earlier point, I talked about change detection, and I alluded to change blindness, even though I didn't actually demonstrate it here in the lecture, but I pointed you, I believe, to web pages where you can look that up. And those would be phenomena where you make a mistake, a perceptual mistake in the sense that there is something out in the world and you don't actually see that. You see something wrong, something that is actually caused by your memory. And there will be a case where an intention like that can fail, that is, the condition of satisfaction is not achieved, and that shows that it's not actually trivial to have a condition of satisfaction like that. So you can see that already reaches a lot of things. And then if you're aware of different levels at which this can happen, as Searle called these psychological modes, he defined 6 such modes. And I'm not sure how serious he is about analyzing psychology, analyzing the structure of the mind that way. There's a lot more structure than these 6 sort of landmarks, but we're using these terms here in this model. And you will see in the implementation that there's a lot of substructure there. Then you can perhaps see the reach of these concepts. For instance, among the mind to world, so the perceptual kinds of intentional states. Perception is the obvious one that I just talked about, but you could also think of memory of being of that nature. Memory meaning you have some mental state that is about things out in the world that are not currently available to your sensors, but that you experienced earlier. And belief would be a more generalized form of that kind of intentionality. So, for instance, to believe that the week has 7 days, or he always gives this example of who's the U.S. president. That is knowledge, and it's about the world, so it's satisfied if it's true. For instance, if you think that Biden is the president, we will say that's true. If you think that Trump is president, maybe that's a mistake. So the condition of satisfaction isn't trivial. And in Searle's discourse, in our own, these things at the belief level are propositions because they have these truth values, the condition of satisfaction. And we actually often think of them as being at a level of categorical concepts, so they generalize somewhat, so that they are not tied to very specific perceptual experiences. So that covers a lot of ground, you can imagine, right? And then the more intuitive intention, word to mind, he talks about intention in action. And that would be really sort of the motor behavior. So ongoing intention action would be, where you're bringing about change right there. You're using your actuators to bring about change, like you move your arm or you shoot the ball or things like that. And prior intention would be essentially something like plans for action, but you can't yet realize that. For instance, you might have a prior intention of driving to the university, which I don't actually right now, but if you have that, then that maybe requires a number of steps that you have to do, and you cannot actually start it yet. You first have to maybe find your car key, or maybe dress and put on shoes and whatever. And so it's an intention that ultimately will lead to motor action, but that requires a couple of steps. And we translate that in our work as essentially sequences of actions and strategies and things like that. And the highest level would be desires, or motivations or goals, what it is that you want to achieve. And again, when you achieve it, then something in the world would be the case. And that's why it has that kind of condition of satisfaction. So even though this is a philosopher's crude categorization, doesn't match exactly onto terms of artificial intelligence, cognitive science, psychology, but one can actually map it. And in our ongoing work, we're actually doing that. We just submitted the grant proposal that lifts some of the stuff I will show you here at these lower 4 levels, low in terms of close to sensor motor, to these higher levels. So these modes reflect the embodiment stance that I make a big fuss about. Remember at the very beginning, I talked about sensory motor forms of cognition, and you can see perhaps that these modes are sort of organized along the distance from the sensory motor surface. So you could think of perception and intention action as being really very sensory motor forms of cognition, where you would have, actions could be active perception, gaze, attentional selection. You would have working memory. Actually, for us, working memory is a form of perception. It's not actually yet memory. Memory would be perhaps something about episodes where you remember certain things you did, or semantic memory, where you know everything that's associated with something being a ball or something being a player, and so on. And prior intentions would show up here, of course, because when you're running, that's your intention action, and your prior intention might be to reach the ball, for which one thing is to run and maybe to kick the ball, and so you're doing a sequence of actions to achieve that. And you might have overall goals. You might have a desire, I don't know, to win or to impress your audience or whatever it is, and you might have beliefs. Maybe you know the rules of the game, or you have some knowledge about how to bring about certain outcomes, and you're using that. So can make sense of these modes in a picture like that. So here is our very toy example of a simplest intentional agent that we built with dynamical field theory. So this is Jan Tekülve's thesis project. It took a very long time to come up with the right example that is simple enough so we can build everything in neural dynamics. And the solutions that I'll show you is one big neural dynamic systems built in CEDAR that you're familiar with now. And it is actually a huge architecture. I'll show you some highlights of it, even though the scenario is highly simplified. And so the world, this is simulated in a robotic simulator, WebBots. This is one of the robots, a KUKA vehicle with a KUKA arm. It's just for illustration. So we're really using some very low level aspects of it. We're using the capacity here of this vehicle to move. It only moves along one line along these objects here. So it's a one-dimensional world for the vehicle movement. It can actually move that arm. We're doing a real movement of the arm. I'll show you. I actually forgot to list that here. Oh no, the reach movement, yes. And it can move toward these objects, and there are some actions, namely picking up color from the paint from these objects and applying paint. And that's just a symbolic thing. That is, we haven't implemented that other than saying that it's a state of getting color painted or applying paint. So you could have like maybe a little spray tool or something like that, or a tool to suck up paint, but we didn't simulate that. So that's the actions this vehicle has. It is in a world that consists of objects that have color. It has color perception, this vehicle, and actually we arbitrarily assign some feature of these objects to function. We made the tall objects being paint buckets from which you can retrieve paint, and the small objects canvases onto which you can apply paint. It would have been more logical, I think, to make the tall ones the canvases that you paint and the small ones the buckets. But for some reason, initially we set it that way and then we didn't change. So it's a little bit counterintuitive that the paint buckets are the big things and the canvases are the small things. So it can, the perceptual system consists of a camera. It has a simulated camera, and in that camera it extracts color as a feature and the height of the object as a feature. There's a simple filter for doing that. So that's sort of the scenario on how we do that. Now, I mentioned motor intentions. These are the lowest level kind of functions, intentional states that will design. These are the lowest kinds of actions, and then we'll have the system develop a scene memory, very limited, and we'll have it have a couple of sequences of actions that we design. So for instance, it can search for an object to paint. It can search for a paint bucket to load paint. It can reach to then apply paint, which is a sequence, and it can move to a record location, a couple of things like that. And then the highest levels, we were really interested here in the beliefs. While the desires are trivial, the desire is really just to have a certain kind of color in the visual array, to look at an object of a color. And so we just arbitrarily assume that the system wants yellow, let's say. So we're now interested in more elaborate ideas about that level. So the beliefs is something we looked at. And so the beliefs are about this knowledge about the world, here about contingencies in the world, and the particular beliefs this system is supposed to have and then actually to acquire and also to use are the rules of color combination. So what we'll have is that in this world, when you apply, let's say, blue paint to a pink canvas surface, you will get something else, maybe yellow. So we use the color rules that are not real rules, so some arbitrary rules, and the vehicle needs to find out about those. And when it knows about those, it has formed a belief. These are concepts, color concepts. It can apply to objects that fall within the categories of the beliefs generalized in that sense. Wherever the object is and whatever its precise color is, but we didn't actually really make much out of that. It's not so important. And so it can then apply these beliefs to achieve particular colors that it desires. That's the goal. So here's the neurodynamic architecture that does all that. So you see from the bottom to the top, you go from these lowest modes, the intention, action, and perception, to the memory prior intention level, to the belief and desire level. So the desire level is trivial, just consists of a field where you put in from the outside a peak at a particular color. That's how it has a desire for a particular color. I'll take you through this now bottom up and show you a little bit what is inside. So all of these are just neurodynamic fields and nodes of different dimensionality, and doing all these actions. And here at the bottom is sort of our sensory motor implementation. Some of those are just pieces of computer code in the simulator. Some of those are, it's a little mathematics in there, like how the wheels work and so on. So here, let's start with action. That's something very concrete that we all understand. So there is a representation of where you want to go in the world, so motor representation that will act on the wheels. Visual search is actually a motor kind, is a world to mind directional fit. It's perhaps a little bit surprising initially, but what you want to achieve a particular state in your system that matches your intention. For instance, if you want to visually select a not tall, like a small object of a certain color, then you have to do a sequence of actions until you have that color, an object of that color in your visual array. So that's a motor kind of activity, a world to mind kind of activity. So there is a mechanism of selection for attentional selection. This is a system for the arm to reach. We actually have a full reaching architecture. I'll show you that in a moment in here, even though we could have done that much simpler, but we actually wanted, there's a point to do that interacts with the arm. And then we have these symbolic things that the painting device just has binary states it can pick up or dispense color, and we just have computer code where we change the color of the object, and then that's connected to a binary node that says, yes, I've dispensed paint or not. So let's look at this intention in action for reaching inside. And now you perhaps get a sense for what this does. This is a movement architecture that actually, some of that was discussed in the summer semester. We didn't do all of this in the winter semester. So it's a simplified version, a caricature of our model of human object-oriented reaching movements. So there's some connection to attention, where when you have attentionally selected an object that has the desired features, its location can be read into this reach target field, where a peak that has coordinates, horizontal along this track, and how far away from the vehicle, a two-dimensional description of the object. We didn't include the height as a parameter, just points at the object. There is some sequential organization that is only under a precondition node, remember, for sequence generation. So only under the appropriate conditions will this reach be activated. It's, for instance, part of the collect or apply paint operation. That's when you want to use the arm. And it is inhibited if some other conditions. For instance, if you don't yet have an object, an appropriate object in the attention foreground, it can't be activated. So when attention visual search has been successful, the conditional satisfaction inhibits this precondition node, and that enables the reach to start. And then you also have to have the intention of collecting or applying paint. There is a movement generation device, which again, in this semester, we didn't really explain a lot. So when there is a peak here, there will be a oscillator created. And here the It's also actually a two-layer neural network. It's actually just discrete one node with an inhibitory node, and that can generate an active transient that just makes a time course that will drive the end effector to the target. And in is the coordinates of that, so the amplitude of that, and cycle time isn't actually varied here, is computed from the target and the initial position of the end effector. So these two, with a coordinate transform in here, extract essentially the hand-centered representation of the target. So how far, in which direction, and how far do you have to, what's the amplitude and what's the direction? There's two coordinates of the movement that are parameters to that movement, and they provide parameters for this oscillator. And then there is a matrix connecting to this representation that with some weights that we tuned by hand that actually computes the different joint angles in the arm that would generate a desired velocity for the end effector as part of that path. And we're sensing the joints. It's just simulated, right? So we can read the joint angles from the simulator and integrate forward, and therefore estimate where the arm currently is, and under the right conditions, that is actually used to update the initial position of the hand. So when the hand has moved to a certain location, then we are done. Actually, this system has two separate actions for extending the arm and then for retracting the arm. These are the two systems in here. But you don't need to understand that fully. I just want to show you the spirit, right? That inside there are all these coupled neural fields, and some of them have different dimensions, and there are two-layer fields that make these oscillations and so on. It's all just continuous. There's no algorithm that starts and stops something. It's all these dynamics that you're familiar with now, where one triggers the next, and the conditions of satisfaction are critical for moving on to the next behavior. So when I say algorithmic here for the applying paint and so on, that's just the motor part of it. In the physical world, the motor, when I have to activate the intention to dispense paint, then the simulator just returns, yes, have done that, and this system goes on. But all the behavior is generated by these neurodynamic equations. So here's an example of the vehicle moving to a location, and then you see it is extending its arm, and then it would be applying that paint, or picking up, in this case, picking up the paint. And so again, the sequence, the fact that it stops and then it does something, it's actually not dispensing, I believe, the paint. And there you see the object change color abruptly, right? And that's the part. So for instance, that the arm is now retracted, and the transitions, all of that is from the instabilities that you're familiar with, right? This is just running continuously numerically simulation of that entire architecture, right? There's no error. That's the point that we're trying to make here. So the perceptual system analogously has, physical sensors, simulated, of course, and the associated neural representation. So the core of it is the feature extraction, so space over, feature space, color, and height of the object over retinal coordinates along this one-dimensional plane. So in camera coordinates, it has some sensors for where the vehicle is, or some sort of dead reckoning kind of sensor, and it has a change detector. So it's also built neurally, that it can actually find that there is color change from a physical transient detector, and it has some state variables if the paint bucket or the can that it has is full or empty. That's just simulated, and has a arm proprioception. There's a neural field where the position of the hand is represented, of the current position of the hand. That's the same field that you saw on the other side. And I highlight here just the scene memory from that. Here, this part, which is a mini version of what we discussed, I think, 2 lectures ago. It's the Grieben et al. Architecture for visual attention and scene representation. So it has these feature space maps, for instance, color space and height in space, and it has salience maps, and it can do selection based on salience, but it can also do visual search. That is, if you have a search queue, it can drive this to select an object with matching feature value. You can systematically search by inhibiting those objects already visited. So it can be used by various different kinds of behaviors, like an explore behavior, a visual search behavior. Explore is building the map and has different connections to other behaviors, like it can read out the selected location and so on. For instance, it can tell the system that it knows where an object of a certain color is and so on. I don't want to go through that the same level of detail. So, okay, so a few limited simulations just to illustrate a little bit. So this is the current view of the vehicle. This is a salience map in which it will be selecting an object. And now I have this thing here at the bottom. So if I go back a little, then you'll see here, so far it has nothing in memory. This is the space feature memories for color. So space color memory over space nothing, and this space height memory, the 2 heights nothing. And here's where, the current selection. So it's currently hasn't built any object. And you see in the salience map that here the leftmost object has a little bit more salience based on something, I don't know what it is. And that will be winning the competition. So there's a peak being formed here. So it will be attending to this object. So what it should do is build a green peak here. And that's a small object. So it should build a green peak up here. And it will do that by first selecting that here. So the spatial salience is showing up now as a ridge here. I don't know for which reason it is here on the left. Should be maybe the coordinates are inverted. So let's just see. So here the object came up, small object that's green, and it's being put into memory. Here's the green, here's the yellow. And that triggers some inhibition of return. And so the salience map this is inhibited, and it will now select the rightmost object, putting up the ridge in here. And then you get an entry at yellow and tall. That would be this object, right? And the answer to my puzzle is that the space we see here is retinal space, while this is the world space. So the vehicle is currently very much here on the right, looking at these objects, and that's why in its world map it's entering here on the right. And if it moved, further to the left, then these entries would be somewhere here. So it's also doing a coordinate transform in the way that you're familiar with. That's based on its current estimate of the vehicle position in that world. And all of that is coordinated by intentions. Yet here's the intention to visually explore, and then a condition of satisfaction whenever it has entered an element into working memory, and that triggers the system to then restart its exploration. Okay. Now, so far it's just repackaging stuff that we've done. Actually, I don't think I have any detail on the prior intentions. So the prior intentions are binding together different behaviors with these precondition nodes that you've seen previously. So I didn't really explore that here. Now, the intentional belief system is maybe the more innovative aspect here. It does some form of autonomous learning that I haven't elaborated very strongly here in the course. So what it's about, the belief system is about triples of color concepts. Here's all color, so it's very simplified. So you have different nodes that stand for different colors, red, green, whatever that is, and so on. So each concept node, remember, is really just projecting onto a certain region in color space, very simple. And so these 3 different sets of neurons with corresponding fields refer to 3 different colors perceived under different circumstances. So this is the color of the paint. We call it here code, like coat of paint for some reason. We should call it paint. So that's the paint you pick up. Now in German, it's actually the same word. Farbe is the appearance, but also it's the matter, right? How you paint something. In English, there are two different words for that: paint and color. And the coat of paint is a jargon for that. And so this is the color of the canvas. And so by how this is connected to the rest of the architecture, we make sure that the peak here is guiding the selection of a canvas, or it is the color of a canvas that we perceive. And same for the coat. And this is the outcome color. So the way it's wired up, as you'll see in a moment, is that color percepts enter here after you painted something, you applied paint, and you get change detection of the paint, then the peak will enter here. And so the triple association that you learn is that, applying, let's say, this funny green to blue gives you, I don't know, cyan. It's actually not so clear. Oh, no, sorry. It was here, this green here, apply that to blue would give you, whatever that color is. And there are discrete nodes up here, which we call belief nodes, that learn these associations. So for instance, by a mechanism I'll show you in a moment, belief number 3 might be activated, this node, and then its connections to the active nodes here will be learned, but Hebbian learning, and therefore this belief will represent that belief of color combination. And the desire as a representation of outcome will be able, under some circumstances, to set a peak here in the outcome. Then it's a desired outcome, and then you can look for what belief to activate. And I'll show you that in a moment. So here's a blow up of that belief system. That has a lot of connectivity. It's quite much more complex than you might first expect it to be, and I'm not going to explain everything about that. For those who know a little bit about neural network learning, this is a architecture that's roughly inspired by the Carpenter-Grossberg ART, adaptive resonance theory, ART architecture. And that was actually one of the first, and still probably main architecture that in which learning is autonomous, in the sense that you're really selecting during the learning the neurons that will be standing for something. And then you organize that when you learn something new, you're not overriding the previously learned thing and open a new piece of neural infrastructure for that. And for that purpose, every belief node is associated with a commit node that represents whether or not that belief node is already committed to a particular belief. So you have to learn not only the belief, but also that you have the belief. Let's say, one thing I want to explain about that is that the connections here, these dotted lines, they are, a priori, there's an all-to-all connection here, and the system is learning a particular set by Hebbian learning. That is, when a belief node is active, and in each of those corresponding node is active, then the Hebbian learning will drive that weight up. And if we do a single shot, that is in a single experience like that, the weights would saturate at the maximum value. But that learning only takes place if a reward signal is present. So there is a reward signal as a modulator of that learning. And that reward signal, which also plays a role here that I'll skip over here, that reward signal is intrinsically generated. It's not from the outside. It's generated by that system, and it is generated from, it's sort of a peak detector. It requires a couple of things to be the case for that signal to say, now I'm being rewarded. That is, now I have a learning episode. So here that episode will be triggered when all these slots are filled. That is, there is some paint color, and you have the corresponding state variable to say, we call it code here, but it's paint. That is, I have some particular paint of a particular color in my spray can. I have a particular canvas color in front of me. So I have an object of that color that my arm is positioned in front of. With all, from the architecture, I can get that sensory information. And I detect a change in the um, in the visual array. So the object I'm intending to just changed color, and then I know also which color that is, the result color. So under those conditions, the reward signal comes on, and it's at that moment in time that the weights are updated. It's the reward signal is actually an active transient, so it comes on for a well-defined amount of time. It's like an oscillator that turns itself off after one oscillation, and that will give the weights enough time to saturate, and then it's done. Then the learning wheel is over, and all the decays move on to the next state. That's the quick summary. There are a couple more subtleties you have to know about normalization. So do we be sure that you can count how many neurons have to be active for each case, and you have to select the free node and a couple of things, so that I'll not go more deeply into. So here I want to show you a few cases of how this works. So here is the system learning a new belief. In fact, this is a case where there were no initial beliefs. So here you see the belief nodes. They're all at negative levels of activation. And these are the weights. So from the belief node number 1 to all the different colors for code, all the different colors for canvas, and all the different colors for weights. That's just for node number 1. And we'll arrange here that it's node number 1 that's selected when there's no other node present. And you have similar weights for all the other nodes. Here you'll see the reward node coming up when change detection is in the scene. This is the change detector itself. You will see where it detects color change. And this is the current view of the object, and it's applying paint here to this yellow cube, I believe, and the paint is actually blue. It has already in its can a blue paint, probably from an earlier experience. And then maybe draw this here by hand first. So you see now the, okay, first let me say that you see here it's yellow, the canvas is yellow, and it's actually when that action is triggered that yellow from some other representation enters into the canvas color slot. Oops, sorry. Right here. See, enters here into slot. So you're building a yellow peak based on that color, but at the same time, as you just saw, the object actually changes color, right? Because you're applying that blue paint you have to the yellow object, you get pink. And again, after a little while, pink comes up here into the results field, the change detector fired. And now the reward signal will be coming up in a moment. Actually, the reward, here it comes, and it through a mechanism that is, in this initial instance, it's biased such the node number 1 is less inhibited than all the others. In general, it would be a free node, a node that hasn't yet been committed, that would be coming up. So here's node number 1 that is coming up. And now the weights of the node number 1 are learning, and they actually learn to saturation here to 1 in this single episode. And so they encode the connection from V1 to blue paint, yellow canvas, and purple outcome. And then the reward resets and the system's open to do its next operation. That's how the learning occurs. And here is how you activate a belief. So it's actually just activated here based on desire. You build a desire peak. The desire goes into the result color peak, and then you're finding the belief node that has that color. And actually, it turns out there are several ones, and it's just selecting one of those. So it has learned already that these 3 here, and one of those is just activated, and therefore it activates the corresponding, the things that it has learned about that. And now these fields can, bidirectional connections, they can actually now drive visual search. You're going to now look for a paint bucket of whatever, this pink color, and for a canvas of that color, and then you will try to make, apply the paint, get this outcome, and therefore you will fulfill your desire like that. The architecture is more complex. It can also recognize that it doesn't need to paint. It already has a object of the right color in the visual array. So this will only occur under conditions where it has decided to have to produce the object by paint by a paint operation. And so here's just one little episode where the vehicle is currently looking for an object. I think it's looking for a tall pink object to pick up pink paint, and the pink is in memory somewhere, I guess. We'll see that in a moment. It's some visual. No, I should say it has a scene memory. See, these are memory traces from which you can bring up the peaks, and these memory traces you see here for pink, it knows that there are two pink objects, and it wants a pink tall one, and the tall one is, I guess, this one here. So it should be activating this one here, I believe, which is a pink tall object, must be here, this one, to pick up the paint. And so here's the cue for visual search is looking for objects of this nature, and here the visual search actually can occur in the scene memory. The condition of satisfaction tells it that that's the case. So it drives up to the blue. You see there, it's reached the blue, and now it's going to actually activate, I believe, the picking up paint operation. Yeah, there, and picks up the paint. And I don't know if we have a neural representation of the node for that. And here in this, oh no, actually, there's another slide where you can see how it then applies it to something else. Or was that here at the very end? Did I? No. So in some other simulation, it then goes and applies that paint somewhere else. Okay. Obviously, there's a whole PhD thesis about that. That's only partially published. We published the autonomous learning part and a very crude description of the whole system. So it's part of our ongoing research project that we're now extending actually currently to essentially to problem solving, to achieving goals that require multiple steps. And so our vision is that we can generalize create all these intentional states as neural attractors in the sense you're familiar with, which emerge and might be suppressed again through instabilities, as you're familiar with, and the condition of satisfaction steers that. And so one of the insights was that condition of satisfaction, as described by Searle and others, that's sort of a logical condition that describes, what the meaning of an intention is. It's defined by its condition of satisfaction. There are two directions of fit and so on. Well, what we're discovering is that we need a neural mechanism for condition of satisfaction to organize that in time. So to stabilize behavior until it is satisfied. And actually, we're dealing with how to deal with error. So when you're not reaching condition of satisfaction, in some models we had condition of dissatisfaction. We kind of moved away from that and have a better understanding of how we deal with the failure of a intention to become satisfied. And as a result of that thinking, we've discovered that there's a real fundamental difference between the two directions of fit. The motor intentions have that explicit neural representation of condition of satisfaction that I discussed in the sequence generation lecture. And that's a direction in which the outcome of the motor action signals that it's successful and it inhibits the motor action. I want to discuss that basic pairing of the excitatory intentional node and the inhibitory conditional satisfaction node. And so temporally, that means that after you have achieved your action, you're going to deactivate the intention and do the next thing, whatever it is. While at the perceptual end, the temporal structure is different. At the perceptual end, the perceptual state itself is the condition of satisfaction. If you organize the process such that, let's say, a peak only arises at feature values that match the world, and so it's its own condition of satisfaction, and that implies that it has different temporal structure. That is, before you have that intentional state, you don't have a peak and you don't have a condition of satisfaction, and then once you have that, it will actually stay on. So both the condition of satisfaction and the intentional states are stay on as long as you have that state. So if you have a percept, as long as you have that state, if you then have to understand how you get rid of that percept. If you have memory, it's very similar. As long as you have that memory, the condition of satisfaction is there, and you would have to detect that it's no longer valid, for instance, by overriding or updating a work memory, which is a complicated project, because there you have to understand that under which conditions there you should have perceptual evidence for your working memory. And so the object should be visible. And under those circumstances, so you can then update your working memory. And that's something we dealt with in the past. I didn't really report that here so well. So these were the elements. Intentional states are abstractors and conditions of satisfaction. And then we were able to build architectures at these different levels. And this project just has some exemplary placeholders for those. With these psychological modes that sort of span different levels of abstraction. And it's maybe important to think about why that was possible. I did mention it before, that we can just build the whole system from these modules in a way, because they are all attractor dynamics. And that means that one of the fields or nodes that we have there, when it is coupled to all the other nodes in an architecture, then that means that there are inputs to it, that vary now, that depend on other dynamical variables. If you think about it as a dynamical system, you have a lot of variables, states, dimensions of the state space. And if you're looking at a subsystem, the states in the other modules are directly or indirectly show up in the equation or affect the dynamics of one subsystem you're looking at, and that will mean that the equation varies a little bit, or some term being present or not, if it's different from zero or not. And the stability is established for the modules without that coupling, right? And what you need to understand how the system scales is to understand that when you change the equation a little bit by adding terms, let's say, that then stable states tend to persist. Some people call that robustness in the engineering sense. It's what is called in mathematics structural stability. That is, that the attractor states remain stable when you change the equation. Of course, it's only locally true that it's only an infinitesimal change really mathematically is guaranteed to preserve an attractor. Actually, more generally, it preserves the whole bifurcation diagram. So there are limits to that. In practice, we of course do more than infinitesimal, but that's the principle. So these different fields and the different modes that we look at have these different dynamic regimes that we design. We write something, in the architecture. We write here, these labels to these fields, or here, and these are just placeholders for understanding what their dynamic regime is. For instance, that they're selective, they can generate a simple peak, or they can generate sustained peaks. That's their dynamics. That's invariant under all the different couplings, the dynamical states that are elsewhere in the architecture and show up through couplings. And then the way we label the axis reflects that we know that peaks have certain meaning in here. For instance, along this dimension color and along this dimension space, which really just reflects ultimately how inputs arrive into that field. So trace back all the way to the sensory surface. And so that's the other necessary ingredient to make these architectures work, that they have a consistent structure that you do not, for instance, provide to a field like that. Sometimes color as an input, and sometimes, I don't know, height or wheel angle along the same dimension. That will be not a consistent architecture. That will be violating some form of information preservation. It's a principle that's not very explicit in a lot of modeling. It's implicit in the cognitive or neural architecture of the brain. And so for these two reasons, we are able to scale the individual modules into neural architectures of intentionality. There is, of course, the task of establishing the dynamic regimes. It's not 100% true that the parameter values you should choose when you study a system in isolation are the right ones when it receives input. And there is some sort of engineering or homeostasis, if you want, from the nervous system point of view, that is needed to maintain the system in the right mode. And that is something that in accounting for psychophysical data, we often find that those data are best explained if the different components are very close to instability, so are not very robust, actually. while when we engineer this for ourselves, for these demos, we often put the system in very clearly stable regimes so that they are very modular. So the nervous system clearly has a capacity and exploits that to operate close to instabilities, which are the cases where there's most different modules affect each other most. And understanding how that is organized is actually also an interesting challenge. So that's as much as I want to say about this research direction. It's a research direction that we want to expand in the future with this goal that I mentioned at the outset of the course of providing ultimately a language that could build the mind from neural processes. Of course, we will always have a very strongly simplified mind that we'll be dealing with, but we'll be looking at qualitatively, do we have all the components? Is there anything missing? And there's still a lot missing. Okay, with this I close.